Okay. The next part that we would like to address is to handle errors. So at the moment, if we run the command line interface, we start a new game, and I'm being asked to select a new door, I can type in any number in here. I can, for example, type in 5, and it will just continue and tells me, okay, the host opens door number 1. But that doesn't make any sense. So we should be able to detect errors, and we should handle them kind of gracefully. And there's one new concept that I will explain to you, and these are Python exceptions. And they're exactly designed to handle errors in Python. Okay, so error handling in Python. I'm certain you've seen this before. If you do something illegal in Python, for example, if you type in x equals 0 and then you divide 1 over x, you get something like this, right? You get an error message, and the error message is often some kind of error of a specific type. So in this case, it's a 0 division error, because we try to divide something by 0. And then it will show us on which line the error occurred, and then the error name will be shown again together with some kind of description, a more precise description that what has been going on. In this case, it is a division by 0 that happened. So here's another case. So if I try to open a file that doesn't exist, so I try to open hello.txt in reading style, I now get a file not found error. Right? So it's a different type of error that we've seen before, and I get some kind of more descriptive information about the error that occurred. In this case, it couldn't find this file hello.txt. Another error that we often come across is syntax errors. So for example, if I create an array of length 12 and I try to, well, this is actually not a syntax error, but it's an index error. So I'm trying to create an array that is too short, and I try to access an element that is outside. Then I get an index error. Or if I make a syntax error, so this is a function definition down here, but if I don't indent it correctly, right, then I have a syntax error. And again, in Python, what you get is exactly the same. It's handled in exactly the same way. In this case, you get an indentation error telling me that, well, in this case, actually missing parentheses in call to print. So let's move this to Python 3 style. But even now, it's still telling me, okay, I expected an indented block. And only when I fix that, the function will actually, or the Python code will actually succeed. Okay. So what's going on here is that when this error occurs, Python raises an exception, right? And an exception is, there are different types of exceptions. So for example, there's this indentation error, there's a division by 0 error, there are various type of exceptions. Now, we could get away without handling these exceptions by adding if statements all over the place. Right? For example, if I wanted to divide by 0 and I want to handle that case, then I could add an if statement, check if it's not equal to 0, then print out the result, and otherwise print the error message that or handle that case. The problem is that it becomes very clumsy to have all these if statements all over the place. And furthermore, it's very difficult you always have to handle the error in the function in which it occurs. So you need to have these if statements in these places where you're actually dividing by 0. But sometimes it's useful to kind of just run something, for example, to just try to open a file, and if it fails, then I just abort it and continue with something else, rather than first checking if the file exists and then kind of making sure that everything is correct before I start calling a function. So, and this is what Python supports. So basically the idea is that you have these try and except statements in Python. And the way it works is that you start a Python block with try, and then you have some Python statements, and then you can have except blocks afterwards that are being called in case a certain exception is being raised or a certain error is being raised. So for example, in here you might have various different Python statements. Oh, this is annoying. In here you might have various different Python statements that might raise different types of errors. So for example, a IO error if I'm trying to open a file, or maybe a division by zero error. And I can handle these, I can catch these different errors in these except statements in here. So what's going on, if we have a piece of code like this, what is going on is when you run this Python code, it will first run the statements that are defined in the try block. If no exception occurs, then it will just run all the statements in here and continue after the except statements. So then everything went fine. If in here, if an error occurs, if an exception is being raised, then Python will go look into the first except statement and check if that specific error that is being raised is handled in this first except block. If it is, then we run these statements here. If it isn't, then we move on to the next except statement, check if it's handled there. And if so, then we call these statements. If not, then we will actually stop the function at the function where this code lives and is being called, and the exception will be moved up one layer up to the mother function, basically. I'll show you a simple example. So here, again, this is an implementation of 1 over x, where x is equal to 0. In this case, implemented in a robust way. So now I have x equals 0. So this statement is safe. Nothing will go wrong here. So I don't need to wrap this in a try statement. But this one here, 1 divided by float x. So this is a dangerous statement. So I put it into a try block, and then in case an error is being raised in here, I handle it with this except block here, and I just print out divided by 0. And then finally, we will print out let's continue anyway. So now if I run this code, you can see that there's no error anymore. Instead, the output is now divided by 0 because the error has happened in here, but I actually handle it in the except block. And instead of throwing the error, I just print out divided by 0, and then I continue my code as usual. Okay, so if I just type in except here, I catch any kind of errors that are being caught. So here, even if it was here, if I look into it, it was actually not a division by 0 error, but also if this code raised another type of error, it will still print out divided by 0. We can get a bit more information about the specific error that was being caught with this syntax down here. So I can type in exception as e, and now I have in the exception block, I have this object e that is the instance of the exception that was being raised, and I can, for example, print it out. So if I can just print out e, and what I will see is exactly the error message that I got before. So here you can see it's float division by 0, and if I go up here, the beginning of my script, I got exactly the same error here, division by 0. Okay. We can also, as I mentioned before, we can also test for different specific exceptions and handle them differently. So in this case, I define x to be a string with a content 0. And what I try to do now is I try to divide 1 over the floating point value of that string. And now depending on the error that I get, I print out different error messages, or I print out different messages. So if I get a 0 division error, then I got a 0 division error with the error messages. If I get a value error, then I print out these statements. And in all other cases, I just print out, I don't know how to handle this. So in this case, I get a float division by 0 error. Let's try and remove this. Let's just try it 1 divided by the string x. So in this case, I also got an error, but it's not covered by 0 division error. It's not a value error. It's actually an error that we don't know, but it's handled in this particular case here, because this last case here handles all the other ones. If I now remove the handling of all other cases and I just had this, then I see, okay, it's actually what was being raised was a type error, and since I don't handle it, I end up seeing the error message and the program crashes. Okay, you can also have you can catch multiple errors at the same time by not providing except one error, but actually accept and list multiple errors in here. And then if you want to, so Python comes in with various different built-in errors, and you can use the, there's a link here that lists all of them, but we can also ask IPython to list them for us, and you can see there are various different ones. Everything from floating point error, IO error, we've seen this one. Import error is being called if you're trying to import a module that doesn't exist, and so on. So you can handle all these cases. So furthermore, you can also raise your own errors. So in your program, maybe if you have a case where the user doesn't put in the right numbers or the right type as an argument to a function, you can raise an error in your program. And the way you do that is you use the raise syntax here, and it takes as the second argument you pass in the error that you want together with a string that describes what the error is all about. So a more descriptive description of the error. So one case where this might be useful is if you want to change the error message that the user sees. Maybe it actually makes sense if you have a function that divides by 0 to actually get an error message, but maybe you want to change the message a little bit to make it a little bit more useful. And the way you can do that is you wrap the dangerous statement again in a try block, and then you catch the error that you're interested in. So in this case, it's the 0 division error. You print out more information about this error, and then you raise the same error again. So actually the behavior doesn't change, but you've added more useful information to the user. So in this case, I tell the user how to use this function. So the input arguments to double invert may not be 1 or -1. So now if I try to call this double invert for 1.1, then that's fine. But if I try to call it for 1, I get the error being raised, but I also get some kind of information of what I've done incorrectly. Okay, and then finally, we can actually create our own exceptions. So I mentioned that Python comes with various different types of errors, but sometimes it's useful to make our own ones. And the way you do that is that you create a new class and you derive that class from the exception class that comes in Python. And so in this simple example here, I just implemented the init function that takes in a message and stores it as a class variable. And whenever this error is being printed, so this is the string representation of my class, I print out some kind of my personalized error message. And then what I can do is I can raise this my error with the syntax down here. So let's try it out. And so indeed, I now raised successfully my own error, and I can print it out, and I get the nice error message that I've created. I can also not wrap this in a try statement and just raise my error. And you can see, yeah, it's my own error that was being raised. Okay. And so finally, we have the last thing that you need to understand with raising these errors is how they're being passed on when you have nested functions. So in this particular example, we call divide list. Divide list internally calls divide string, and divide string internally calls divide, and divide is the one that divides 1 over x. Right? And so now if the exception occurs in here, and if it's not handled here, then the execution of this function will stop, and the exception will be passed on to the function that has been calling it. So in this case, in divide string. And if again divide string doesn't handle this exception, then the exception will be passed on to divide list. And if divide list doesn't handle it, it will be passed on to the main function. And also if the main function doesn't handle it, then the program will exit. Right? And so now it's up to you to decide where in that function stack you should handle this exception, or if you should not handle it at all and just exit the function. So you could decide to, well, I want to make my divide function more robust, and I just handle the exception in here. But maybe it's actually a good idea to have a divide function that crashes when you divide it when you try to divide something by 0. So then you could argue, well, maybe I should make the divide string function more robust or the divide list function more robust. So actually, maybe I should just add the try statement around here. Right? So all of these are valid. All of these are actually valid choices, and really depends on. It really depends on your use cases and on your program. What is a good choice? Okay. So so this is how you handle errors in Python. And let's see how I've implemented error handling in our Monty Hall Python script. What I've done is, this is now step number 4. So I've done 2 things. So first of all, I thought it might be a good idea to implement my own exception. And so basically I called this exception invalid game input. And I'm going to raise this every single time when the user types in an invalid input. And so really it doesn't do very much. So I just derive from the exception class, and I have my init function that takes in the message, and then the string representation is it's just literally the string representation. So it's basically an empty class. The only difference that I have a nice name on here. I call it invalid game input, which will make more sense when you read the code where I raise this. Okay, and then the actual implementation now, in the actual implementation of our module, we now import this specific exception, the invalid game input exception up here, and we erase it whenever the user does something that is not valid. So for example, when the user selects a door, and the door is not between 1 and 3, then I erase an invalid game input with the description door must be an integer between 1 and 3, and you provided a wrong number. Or if the user selects a door, the same door that is already opened, I also raise an invalid game input and with the error message cannot select open door. Yeah, and so I basically, in all these functions, I just went through and tried to catch the most common errors that the user will make. Okay, but so far we've only raised the errors, but we actually didn't handle them anywhere. We didn't catch them anywhere. And this I now added to the command line interface. And basically, I try to keep it very simple. I just wanted to, if the user does something wrong, then we just abort the game and start a new one. And so what I've done is I wrapped the entire game statements in a try block. And at the end, if the invalid game input exception is being raised, then I just print out the error messages, print out that I'm restarting the game, and because everything is in a while loop, it just continues with the new game. Does that make sense? Yeah? Okay, so the next part is, so you've got a lot of things now. We've modularized our code, we added documentation, we added a project website, we handle errors, and so the next thing is we want to add tests. We want to make sure that if other people use our code, change our code, that the core functionality is not being broken. And so the way we do that is, I chose PyTest here. So I created a new directory, a new folder called tests, and a new file called test_module.py, and that implements all the tests that I want to have, or some kind of basic testing. So let's look at that. So what am I testing? So, well, I import the modules that I'm interested in, and so this is how I typically write tests. So so basically it's just a list of functions that tests one specific part of my program. And then I have asserts at the end. So I have some statements and then I have an assert at the end that I want to make sure this assert is always valid, is always true. And so these function names up here, it doesn't really matter what you call them. PyTest will just go through one after the other and call them and make sure that they succeed. But it does make sense to kind of have a descriptive name because this will be part of, if an error occurs, then PyTest will actually print out this function name. And so one naming strategy that I kind of find useful is if you make it almost like a sentence. So I chose test that a normal game wins or loses. Right? So it's just, this just runs a normal game, and I check that, well, the player either loses or wins, and nothing else. And so you can see the code is basically just creating a new game, selecting the doors, opening them, and so on and so forth. And at the end, I open my door, and I check that either the return variable here is either true or it's false. Right? That's it. Then I have a very simple test here where I just check that if I call the statistics function, that I get a string in this case. So it's a very weak test, yeah. But at least it tests that the statistics functions works in some sense. And so what I'm doing here is, because in order to have statistics, I need to have a few games. So I just call the test that normal game wins or loses function 10 times. So this will generate some statistics, and then I call the statistics function. And then also it's quite useful to have to test invalid inputs. So here, the last test tests that selecting an invalid door raises the correct exception. And so in this test, I create a new game, and then I try to select door number 4. But because I know that this is supposed to fail, I wrapped it into an except statement where I catch invalid game input. And in this case, I just pass over it. So I ignore exceptions like this. So now if this, I see this test isn't actually so good. So I should make sure that this, what I should really do is I should have an assert false here. Because I never want to get to this case. I never want to get to this line because the exception should have happened on this line, which then makes Python to jump over here and I finish the function successfully. But if this line actually succeeds, then I will now hit assert false and the test will fail. Does it make sense? Okay. And so you just go ahead and implement some tests, and then the way you can run them is with this command here, python -m pytest tests. And you run them, and in this case we have the 3 tests, and they actually pass. So that's good. And so there's this minus v flag that makes the test more verbose. And this is what I meant. It's quite useful to have descriptive test names, because now you can see, just by reading out the function names, you can see what the tests actually do. And if they fail, you kind of know immediately, maybe just by looking at this output, what was going on. Okay, last step, we are almost there. We want to add some installation files and instructions so that it's easy to install our package. So the first thing that we've already done multiple times before is to create a setup.py file, which I've shown here. So it's, in my case, it's a very simple file. The only important thing really is this packages equals Monty Hall game. So this is the directory that contains the module that I want to have installed when I call Python setup.py install. So once you've done this, you can type in Python setup.py install in that package directory, and it will install the package for you. Actually, even better is if you use the Python package manager called pip. And it does the same thing, so you can type in pip install dot, where the dot just points to the current directory, so you want to install the current project. And the reason why pip is useful is because you can also uninstall stuff again. So once if you installed your package, you can then call pip uninstall Monty Hall game to remove the package again. So just a small hint. Then the last thing that we need is so our project has some dependencies now, right? We know that if you want to successfully run that project, you need to have Flask installed, and you have to have PyTest and Sphinx installed. So Python comes with a way to document these dependencies, and typically one saves them in a file called requirements.txt, and one just lists these dependencies in these files. So this, I'm just printing out the file content here. So I'm stating I need, if you want to, it's dependencies, I need Flask, PyTest, and Sphinx. And then what the user is supposed to do, the user is supposed to type in pip install -r, and then this requirements.txt file. And what that will do, it will install all these packages and all the dependencies that these packages have. Right? So Flask again has various different dependencies, but they're automatically being installed as well. So if I run this, you can see that there's actually loads of packages that are being in this case, it actually just says requirement already satisfied, so it doesn't install anything new, but it would install quite a few packages in this case. And then I also well, what is quite good practice if you add an install file in your project. So there you can just, it's just a simple text file that explains how you can install the package. So in my case, the installation consists of 2 steps. You first need to install these dependencies with pip install -r requirements.txt, and then you can install the game with pip install. Okay, so then we have following new files. We have the install file, which is just a text file with some installation instructions. We have the requirements.txt file that lists the project dependencies. And then we have the setup.py file that is the setup tools file. And then this is now our final project layout. So we started with a simple script, just a simple.py file and some templates. And this is now our final project folder. You can see it has grown quite massively. But let's just go through it again to get an overview. So we have these installation files, install requirements txt and setup.py. They can just live in the main folder. Then we have the module files. So this is the main modules that we've implemented. The name is the name of the directory should be the name of the module. Then we have an init file and all the Python implementations that we want. Then we created the spin directory that contains all the scripts. So these are all the runtime scripts, for example, the command line interface and the web interface. So they're all stored in here. Then we have some additional templates files that we need for the Flask application. Then we have this doc folder that contains various different files, but all of them have been automatically generated by Sphinx, so we didn't have to do very much. But they should also belong to our repository. And then finally we have this tests folder where we add all the PyTests. In this case, I just have a single file, but potentially there might be many files in there. Make sense? Okay. So you'll see this. So this is kind of quite a common structure, and you'll see this in a lot of projects that you come across, or at least in some way or the other. Okay, any questions regarding moving from a script to a project? It's all clear? Maybe? Okay. So we have 15 more minutes. I would like to show you a concept that I've used so far in Python, but that I haven't really explained. It's called Decorators. And so there are these add symbols that you've seen sometimes. So you know when you define a function, and then before that function we had add number, for example, and that automatically did this JIT compilation. So this add symbol that you have in front of a function, that's a decorator. And you sometimes see this, and it's good to understand why it does. And it's actually quite a neat trick for some cases to make code a lot more readable and a lot more flexible. Okay, so this is something completely different now. It's just one more Python sugar syntax that you can use for your projects. All right, so we're talking about functions, and remember that in Python, functions are just normal objects. So if I create a function, if I define a function add, and I check if that function is an instance of object, then Python tells me that this is indeed true. As a consequence, what I can do is I can pass functions into functions. So look at this example. I define 2 functions. One is called add, that adds 2 numbers. One is called sub, that subtracts 2 numbers. And I define another function called apply that takes in a function and it takes two arguments of that function. And then what I do inside is I just call that function with these two arguments. Okay? So I accepted, I got passed in a function as an argument, and I just used it inside the code just as if it was just as it is a normal function. And so now what I can do is I can call apply and pass in add. So this add function here, I pass in as the first argument 1 and 2, and the return value will be 3 because I'm calling add with the arguments 1 and 2, so these two numbers are being added, and apply returns the return value of that function, which is 3. I can also call apply to sub, in this case 7 and 5, and then the sub function is being called with the arguments 7 and 5, and I get the result 2. So that's one thing. So we can pass in functions as arguments. We can also define functions inside functions. So in here, we now have a function g that takes in 2 arguments. Inside that function definition, I actually define another function called cube. It takes in 1 argument, it returns the cube of that argument. And then my function g uses that, just calls this function cube in here and makes use of its return statement. So this function cubase will be only available in the namespace of g. Outside here, I won't have access to this cube anymore. So it's a function that just lives as part of another function. Okay, so that's maybe not so surprising that we can define functions and call them inside, but we can also make functions return functions. Right? So we're almost building functions now. So what I can do is I can define a function h that just takes in a message. In that function definition, I define a new function called inner h, and so now I personalize this function, or I specialize this function. So I have a print statement, and that print statement now makes use of this message that was passed in to the original h function. Right? So take note that inner h doesn't take any arguments. And this message object here was passed into the h function, not in the inner h function. And so now I constructed my inner h function and I just return it as part of the h function. And so now what I can do is I can call h with a string, so for example, hello moon, and I get the return value of h is inner h, which is a function. Right? So foo is now a function, and I can just call it. It doesn't take any arguments, so I can just call it. And what I get out is the string inside inner h, printing message, and then in this case it's hello moon because this is what I passed in here. So now I wrote a function that generates another function. Okay. So this is, now we're slowly approaching the idea of decorators. So a decorator is a function, it's basically a function that returns another function. So I'll show you, this is kind of the general concept here. So imagine we have a function foo that just returns 1, but we would like to extend that function. We want to wrap that function into another one. So what we do is we write an outer function that takes in the function, that takes in a function, and then inside the outer function we define the inner function, and the inner function does something. It's, for example, some kind of print statements, or and then it returns. Then it calls the function that we passed in and returns its values. And it's this inner function that we then return. So the result is now, if I have a function foo, I can pass the function to outer, and I get a decorated version of that function out. So my original foo function just always returned 1, while this decorated version of the function now, if I call it, if I call it, it prints out before calling func, and then it returns 1. So my decorated version has an additional print statement. I've taken a function, I've extended it a little bit. It keeps its original functionality, but I have extended it with this print statement. So if we wanted to make this cleaner, we could have also just written foo equals outer foo, and so I've basically overwritten foo with the original version. So this is, okay, you might not see the value of this quite yet, so let's, I want to show you a slightly more useful example. So imagine you have this function f of x that returns log of x minus 2. Right? And so you know that the log function is only defined for positive numbers. So if I call this function for 5, then everything works fine. But if I call it for minus 1, then I actually get a value error. And so basically what I want to do now, I want to make a wrapper of that function that first checks the range and prints out an error message in case I pass in the wrong range. And so the way I do that is I implement this check range function. It takes in my original function, and then this is what I construct. This inner function is what I want to construct. It takes in, my inner function takes an argument. It checks if the value of that argument is smaller than 0. In that case, I print out out of range. And otherwise, I call my function and return its value. And it's this decorated function that I now return. And so now what I can do is I can take my original f, so this f here that failed for negative inputs, and I call it onto that check range and overwrite its value. And so this now gives me the decorated version of that function that works for both cases. So I can now call it of f of 5, and I call it for f of minus 1, and I will get the error message that I saw here. And so this decorator syntax is now just a tiny syntax sugar on top of Python to do exactly that. So rather than having to type in f equals check range f, I can just now define a new function, and before that function I type in add and then check range. The check range was this strange wrapper thing that took in a function and returned a function again. And Python will now automatically apply the decorator on that function G. Right? So basically, if I don't have this, and I try to call it, I get a value error. If I add this check range decorator, Python will now automatically wrap G inside this check range decorator. And if I now call G of U, I will get the out of range message. And so the syntax works as follows. You have this add, and then you have the name of the decorator function. Okay, I want to show you an actually useful example for this. So imagine you have a really slow function called, I called it slow. It takes in 2 arguments, it multiplies 2 numbers, and then just to simulate that it's really slow, I also sleep for a second. And then it returns the result of these 2 numbers. So what we can do is we can define it and we can run it, I can time it, and it will tell me, well, this function roughly takes 1 second per loop. Now, there's a concept called memorization. And what memorization does is it, rather than, if I imagine I call this function slow many, many times, but maybe I call it very often with the same input arguments. Now, rather than having to recompute the output variables for the same input variables over and over again, I could just cache them. And before I call the function, I just look in my cache if I have the output variable again already for these input variables. In this case, I just return the value that I have in my cache. And otherwise I actually have to call the function. But I also store the function result in the cache and then return it. This is called memorization. So memorization is a caching for functions. It only works for functions that are that have no side effects. So you can't, if you try this with, when you open a file, for example, this won't work because the file might have changed in the operating system. But for something like this, where we just multiply numbers or do some maths, then that works perfectly fine. Okay, so basically what the idea now is to write a decorator that implements that memorization for us. And the way we do that is we call this decorator memorize. And we also, so we need some kind of cache. So this is a dictionary that will store all the input to output values. So what does our memorize function do? It takes in a function, and we want to decorate that function so that it's memorized. That we first want to check if the output value already exists, and in this case just return that one, and otherwise we need to call it. So let's see what we do. So this is our decorated function up here. It takes in two input variables still, x and y. And what we do, we check, the first thing that we do is we check if x and y, if the tuple x and y is in cache. And if it's in cache, then we just return the cache value. If it's not as part of the cache, then we actually need to call our function func with the two input arguments that we have been given. And we store the results in the results variable here. Then we add the result to the cache variable and go back to the user with the result. And it's this inner function that we now want to return in our decorator. Okay. So now, if we again have our slow implementation, but now I can decorate it with this add memorize decorator. And so now, just by adding this one line, I now have a memorized version of this slow function. And so if I run this again, it's actually still slow. So something didn't work. Let's see. Oh yeah, here we go. Oh yeah, okay. Of course, so I need to run it once to create the cache, and then only it's the second time when I run it when it's going to be fast, right? So first I need to create the cache, and the second time it's going to be fast. So the first time it was really slow, 1 second slow, and now the second time I called it, it was only 2.3.8 microseconds because I was able to use the cache. Okay, so that was another syntax sugar in Python that I wanted to show you. So decorator is a function that takes a function as an argument and returns a modified version of that function. For example, a memorized version of that function. And it's this add decorator syntax that is simply shortcut for calling f equals decorator f. Any questions regarding decorators? No? Okay, then see you next week.